I'm from Bristol, from close to Bristol, tiny little seaside town. And so I grew up next to the sea, although it's a dirty brown sea because it's an estuary, so it's full of mud. But so I spent most of my childhood clambering over rocks. And according to my mother, you know, they'd take me to the beach and she was constantly having to pull me off of cliffs because I was always clambering all over them. But it wasn't until I got to school, when in secondary school, there were two subjects I really enjoyed. There was art, because I really liked drawing, and then there was this new subject, geology, that I started taking. So this was secondary school. So I was about 13 when I first started doing a bit of geology. And it was part of a geography course. And they took us to the beach, which was, you know, a little bit of a field trip. And the teacher showed us how we could look at the shapes in the rock and interpret the past. And we sat there and drew these rocks. And I thought, this is incredible. Because it was unlike other bits of science. I could see what was happening myself. So I could actually do it there and then. I could sit there and see. I remember it was nonconformity, which is this big time gap in rocks. And there in my hometown, it's about a 350 million year time gap. And you can see that the rocks below are truncated by the rocks above. And the very thought that that was a land surface that existed 350 million years ago, and that there were, you know, amphibians crawling around on that surface. I was absolutely fascinated that I could see that with my own eyes. So the subjects I loved. And I had this but I was undecided whether I wanted to do art, become an artist, or an architect, or something in technical drawing, or to follow this science route. And I got to draw in both of them. So geology involved drawing. So eventually I thought, well, I'll do geology because high chance I won't get paid anything as an artist. If only I'd known that scientists aren't exactly fantastically paid. From there was no looking back. I lived and breathed geology, lived and breathed rocks, all the way through, so that when I did my degree, towards the end of the degree, obviously everybody's thinking about what they would like to do for the future. A lot of my friends, you know, they wanted to go off and actually earn some money in industry. But for me, it was absolutely clear. I had to do research. I really wanted to do research. The reason I fell into cosmic dust, and I literally did fall into cosmic dust, was I did a PhD at University College in London, and it was on volcanoes and magmas, and I was doing something called experimental petrology, which is making rocks in a laboratory. This is between 1989 and 1993. Okay. So the PhD was great fun because essentially what you're doing is you're heating up rocks, heating up chemicals, and you're making magma in the laboratory, and then at high pressure, and then you're allowing it to cool, and you get to look at all the lovely minerals that have formed inside that rock and their compositions. And I really enjoyed it. So I decided, right, that's what I want to do as a job. I want to go off and do experimental petrology. And I applied to jobs all around the world, you know, to do this. And I did not get one. Just everywhere. There's two really difficult steps in science. One is going from a PhD to your first postdoc, because there's so much competition. And the second is from becoming a postdoc to getting that permanent position at a university. They are famously difficult because there are so many people wanting to do it. And I couldn't get this job. And I had young kids, and I was married. And you can imagine me not earning money was a bit of a problem. And this job came up at the Natural History Museum to study this stuff called micrometeorites. The job advert was to study micrometeorites with someone called Monica Grady and Robert Hutchison. And I remember going to my interview, because I got an interview. And I remember Bob Hutchison turning around to me and saying, "So what do you know about micrometeorites? Do you know what they are?" And I said, yes, they are small meteorites. And he went, essentially, yes. Because they didn't know either, because it was such a new field. So this was 1994, 5, something like that. And so I started work as a postdoc at the Natural History Museum. And it was great because the first Antarctic micrometeorites were recovered by Michel Moret in Paris. And he collected an awful lot of them, and he was willing to give the museum a whole load of micrometeorites, just material from the Antarctic. So there have been very few papers on them. And so I was looking at this material that was virtually unknown. I think they asked for the material from Michel, and he had quite a lot of it. So he collected over 20,000 particles, which is a lot. You know, that's more than one person can study, or one research group can study. So they gave me some vials of the dust that they collected from the Antarctic. And it's just absolutely packed full. I've never seen, you know, so now I look at my collection is from dust found in a moraine in Antarctica. And there, you know, you pour your dust into a little dish, and you look through the dish. And I usually, in a dish full of dust, find 2 or 3 micrometeorites. In this Caprid-Hom material, melted out of the ice, I would look through the dish and find maybe 100 micrometeorites. That was amazing. They were everywhere. You know, it was a wonderful source of material.
So this was before Susan Taylor, of course. And
yeah, it was ever so. So I remember Susan giving her talk on the discovery of micrometeorites in the South Pole water well. And, you know, that was such wonderful material and such a clever idea as well. There was already a big pocket of water that they had melted out. But the problem, of course, was that there had been a fire in the water well, which sounds bizarre, but in the house, the little house hut sitting above the water well. So there were lots of contaminants, and they were all dark and irregular in shape, which meant it was really difficult to find any unmelted micrometeorites in it. So it was mainly cosmic spherules. But it was a absolutely great collection. And, you know, so I was very lucky to fall by accident into the study of micrometeorites at the very point where all these samples were becoming available. And, of course, the thing you'll be interested in probably is I think it was said to me by Michel that the reason that we go to Antarctica is it's impossible to collect micrometeorites outside of Antarctica. People have tried, but there's so much terrestrial contamination, you just can't do it. Of course, what didn't really help was over the years, there were lots of people who tried. And what they found was huge numbers of metallic spherules, and most of them are terrestrial contamination. And of course, so us as scientists, we were always having people coming to us and saying, I've got a collection of 5,000 spherules, which are micrometeorites I found in the road outside my house. Would you please confirm them? Would you spend the next 5 years of your life confirming my discovery?
It is the same with meteorites. If you are a known meteorite scientist, you will get 2 people who contact you every day.
Yeah, you do. I get lots. Lots and lots. When it's obvious, it's easy. You know, so most of them I think are, and I'm like, no, that's called a quartzite, and it's a bright white colour, and the fact that it's got a little bit of black on it and it's got a strange shape doesn't mean it's a meteorite.
What type of analysis did you do on the Antarctic Moret material to begin with?
Same thing I do now, really, scanning electron microscopy. We worked out how to polish them very early on. I made a big mistake at first, which is such a student thing to do. When I picked the particles, I stuck them onto a stub, and I really spread them out. And the first time I put that in the SEM, I realised I spent hours looking for the other particles. You know, and then, so now I always say to the students, get them as close as you can without touching. And it makes it much easier for polishing as well. And the students are really bad at it. With micrometeorites, I can make patterns. So I once did the Royal School of Mines emblem in micrometeorites on a sample.
When was it obvious that you couldn't use the morphology? You had to do the polishing?
Because I'm a geologist. Yeah? Because geologists Yeah, the outside of the rock is just that weathered rubbish that you don't want to look at. That I was so used to making sections that's where we just immediately went to. Plus, of course, with the instruments I use, it's not possible to do quantitative analyses on the surface, or they are less quantitative because you've got larger uncertainties. So making a polished section allows you to get fairly accurate analyses and actually determine the mineralogy.
Had Moreton established that?
Yeah, and
okay.
I think the year I arrived was when Gero Curat did his paper in '94. Gero was a lovely chap, really, really nice. Another one of these really generous scientists. So he did a wonderful paper, really describing all the micrometeorites in lovely detail. When I published a couple of years later, I heavily relied on his paper.
What was your first publication or article or writing about micrometeorites?
About micrometeorites, I think it was the cosmic football, which was this grazing incident particle. And the reason I called it the cosmic football is I found it during Euro 96. And, well, as I was telling you earlier, you know, funnily enough, that cosmic spherical was the very first micrometeorite I picked, the very first time I looked at this dust. And I when I examined it, I for a long time, I thought all cosmic sphericals should look like this. And it took a while to dawn on me that, no, this was the exception. This was the really interesting one. And then the next paper was on all fine-grained micrometeorites. That's where I started disagreeing with some of the things that Michel was saying, because Michel really firmly believed that the micrometeorites were very different from meteorites, and there were samples of something else out there, potentially comets. Whereas what I saw was they actually looked very similar to components from meteorites, because of course they're really tiny little particles, where a meteorite's really huge. You know, you get millions of micrometeorites into a meteorite. And so you're not sampling, you wouldn't expect to see whole chondrules, and that. So you've actually got to see it in that view. You've got to think, well, these are tiny broken up bits of material. Could they be from asteroids? And the answer I thought was yes. They could mainly be from asteroids.
During these first years, were you collaborating with Michel Moret?
We weren't in contact all the time. No, we weren't in contact that much at all. So Michel had very kindly. I had visited Paris to visit Michel. Michel is a hilarious person. He was quintessentially French. He was like a caricature of a Frenchman.
I read his books, also always talking about what kind of food he had eaten when observing this and that asteroid.
So I remember going to visit, and I was sharing an office, I think, with Cecile, because she was a PhD student at the time. To go to the toilet, I had to walk past Michel's office. And so I was only there for a week, and I would walk past Michel's office, and he would come rushing out and would go, Matthew, where are you going? And I'd be like, I'm going to the loo. And he goes, no, you go to find pretty French ladies, yes? And it was just so funny. And he played, you know, he was playing up to it. And I remember turning around to him and I said, Michel, why don't you go to international conferences anymore? The real reason, and I found this out later, is he was really frightened of flying. So he didn't want to fly, and, you know, most conferences were outside France. And he said, the reason I do not go to conferences anymore is the young ladies are not interested in me anymore. I am too old. I am too old. And I think a couple of years later, I organised a little conference in the UK, and I very specifically invited Michel. And I invited him and said, I will arrange for a couple of pretty young ladies to be present. You know, today, that email would get me in big trouble, would still get me in big trouble if anybody read it. You know, even though it was all in jest. And Michel turned up to that conference. First thing he said to me was, where are they?
Did he talk to you about his early years with Apollo and the moon dust?
No, not really. Not really. I do remember him in the lab, though. he got me to pick, he was training me to pick micrometeorites. And I picked a whole load of cosmic spherules. You know, there's an entire stub with maybe 50 micrometeorites on it. And he looked down the microscope and he went, yes, those are all micrometeorites. And then he took the stub and he threw it in the bin. And he said, oh, they are just melted rubbish. We're not interested in those. Sent a shiver down my spine.
Was that because he was already interested in the carbonaceous ones?
No, that we didn't know about the carbonaceous ones for years and years. His entire focus was on the unmelted micrometeorites. But to me, that was like throwing away data. Eventually, Michel stopped talking to me. When my papers disagreed with what he believed, then eventually I became the enemy, I think. Yeah. So I do remember one conference where he gave a very interesting talk, and I simply stood up and asked a question. I think in the question I said, because we see some particles like this, Michel, in your stuff from Capra-Tom. And he went, no, they're not there. And I said, no, they are there, Michel. He goes, what would you know, you fool? You're a fool, absolute fool. And everybody was laughing, and I'm laughing, because it was actually really very funny. But at the same time, you know, I can handle it. But had I been somebody else, a bit more sensitive, then that could have really destroyed their confidence. Yeah. And everybody knew what Michel was like.
Did you say the proverbial expression that give me a ordinary chondrite and a hammer and
I'll show you some cosmic dust?
Was that you?
Yes, that was me. Yeah. Yeah. He really didn't like that at all. And it's not strictly true.
One of his books is not mentioning your name?
No, of course not. No. But then it's not strictly true. Give me a hammer and an ordinary chondrite and a carbonaceous chondrite, and I'll show you 90% of micrometeorites. But then there's the interesting ones are the bits you don't see in meteorites, because they should all be there. But you need to look at huge numbers of particles to find the really interesting ones. But, you know, Michel was absolutely great. I loved him. I thought he was absolutely fantastic. Despite the fact that he seemed to hate me, I still had massive respect for the guy. He came up with some amazing ideas. Okay, sometimes he wasn't too troubled about facts and evidence to back up those ideas, but there is a place for that in science. The dreamers amongst us who are not constrained by evidence. As long as you convey that this is just speculation, but that's science too.
Can you remember from the same time any other interest in micrometeorites elsewhere? I mean, apart from Paris and Monica Grady.
Yeah, at the time, there was me in the UK, there was Michel and Cécile in France, and then eventually Mathieu Gugnel joined that group too. And then, of course, there were all the guys at the Johnson Space Center who were studying IDPs. So they were mainly interested in the stuff that was collected in the atmosphere. And I don't know why, but for the longest time, we saw those groups really didn't mix. No. And actually, they still don't most of the time. Because there is quite a demarcation between the two. The anhydrous IDPs really don't look much like micrometeorites at all. And there's this difference with size. They do have particles that are like micrometeorites. What always amazes me about the micrometeorites field is how everybody claims their collection is the best. But mine isn't. It's rubbish. It always amazes me that people, you know, they talk about it being the most pristine. And that's like with the Capra-Tom one. You know, it is the most. You get the really nice, lovely, unmelted micrometeorites, ultra-carbonaceous micrometeorites, but hardly any of them. The number of particles they collect are very small because they're melting snow. You know, this point about looking for the really rare particles. You can't do that on that kind of collection. In fact, Michel's old collection from Capra-Tom was far better for finding rare things because there were so many particles. The modelling papers always come up with this very high cometry flux. But you look into them, and usually they require quite a lot of digging to figure out what they're talking about. And it appeared that the vast majority of that was particles less than 50 microns. And I was, well, that's not a problem, because that's all the IDPs. I'm talking about the micrometeorites. There will be some large anhydrous IDPs amongst micrometeorites. It's just they're very rare. So there are some things that have been identified as asteroids that have suddenly started producing gas. So we know. But, you know, all you need is ice. really. So far, I don't think we've got enough data on cometary ice to be able to say. Certainly the comets we've looked at so far, none of them has been an exact match for the Earth. There are one or two asteroids where it's very close. But the weird thing is it's not like we go to asteroids and see that most of them have that composition, because that's what you would expect to see for the Earth's oceans. So no, I don't really have an opinion about it. All I can say is, it's formed from, it's delivered to the Earth.
Let's go back to the end of the 90s when you were starting to publish. How did you get into the classification, by the way?
Some of it already existed.
Yeah,
So Gero Kurat did the bare bones of it. And so I just added to that, and Michelle was classifying things as well. And at a certain point, I just thought, well, we should just all coordinate and agree on what we're going to call them, because that's what a classification system is. It's, a nomenclature that is agreed between everybody who's working on it. It's consensus view. All I did was get everybody together and write the paper and try and make them agree, which was a bit of a challenge sometimes, because people get very attached to the names that they use for things. So an example was I call coarse-grained micrometeorites. So these things that have a fairly large grain size compared to the sample size, and they usually have igneous textures, whereas they called them crystalline. So other groups called them crystalline. And we agreed to call them coarse-grained micrometeorites because we had fine-grained, and these could be the coarse-grained ones. So we wrote that paper together, and then they carried on writing papers calling them crystalline micrometeorites. And that still happens. And neither term is perfect, because they're not coarse-grained. These are small particles. They're not big crystals. And everything is crystalline. We call them igneous, but then cosmic spherules are igneous too. So there's no perfect name you can call things. It's always a good idea if the name you use for something makes it obvious what it is, if it makes sense to people. We could call all fine-grained micrometeorites Jane, and all coarse-grained micrometeorites Bob, and nobody would know what we were talking about. And there was that trend, actually. Did you ever come across this?
Nope.
Amongst the IDP guys, like people like Lindsay Keller?
Yeah.
They went through a funny phase of nicknaming individual particles. And so, they had one that they called Skywalker. It's just yet another name to remember, isn't it?
Have you any number on how many publications related to micrometeorites you have approximately?
Oh, that's a good question. It's terrible, I don't know. I've got 75 publications in all, so I should imagine 60 of those are about micrometeorites, something like that. It's not all that many. I know professors with 200 papers who look at me. Of course, they didn't write any of them, or the majority of them. I like writing papers myself, which is probably why I will never be a professor. I don't fit the mold. I'm not a manager of people. Just ask my ex-PhD students, they'll say, well, I'm not a manager of people. The ones that I'm most proud of about micrometeorites, I quite like novel problems. So I've always been fascinated by the minutiae of, tiny little interesting processes, which is ridiculous, and I shouldn't be, really. So there was one about spinning micrometeorites I really liked, where we saw these micrometeorites with big bubbles and big gas vesicles right in the middle. And I worked out that as they spin, the vesicles head towards the spin axis. And so if they're spinning around a complex axis, they've got two spin axes, they should head towards the middle. And I was particularly proud of that.
Yeah.
I don't know why.
I understand.
I explained why some micrometeorites are hollow. So my PhD student, Isabel, when she was a master's student, she used my model to do some calculations on the forces on metal droplets during deceleration. And they're actually quite low. So they migrate really easily to the front of the particle. But then the deceleration is less than the surface tension of metal on silicate. So if that represents the force you require to separate the metal, you shouldn't separate the metal during deceleration. But if you spin them, you can spin them arbitrarily fast because, you know, the limit to spin is when you get to relativistic spins, because then the torque you require just goes through the roof. But that's so fast. So her project, she concluded that metal separation occurs through spin rather than deceleration. And I've always intended to do this a bit more rigorously, because the weak link there is we just used a simple threshold for the force required for separation, where it's a very complex process. So right now I'm trying to get my head around hydrodynamic simulations so I can simulate two droplets attached to each other and work out how that separation, the threshold for separation, how that relates to surface tension. To work out how fast you need to spin something or decelerate it before you start forming that neck in a silicate liquid. With hydrocode, you should be able to simulate that kind of thing. Another way I've thought of deforming spherules is having vesicles bursting on the surface, because that you know, produces little bits of splatter. But then one thing that I talked about with the spin is, you know, you do separate metal and vesicles very quickly from spherules because of the density difference. But if you spin them around an axis that is 90 degrees to the direction of motion, then you immediately stop losing those vesicles and those metal droplets. Because, of course, they're always trying to separate out. The metal is trying to separate out downwards. You turn the particle over, it's just going to do that around the. It's just going to sit there vibrating around the center of the particle. Because that's the predominant way in which micrometeorites spin, with a spin axis in the direction of motion, because it's the windmill effect. You know, they spin up during atmospheric entry. Whereas if they are at a higher angle to the direction of motion, then it's highly likely that's pre-atmospheric spin. So that's what I said in that paper too. And you know, that one got rejected from geology. And they wrote back to me and they said, why should we be interested in the spin of dust in space? Quite important when it comes to polarization. It's just these blinkered scientists who just go, well, that's trivial. That's not interesting. When you look at a micrometeorite, if there are more flat faces pointing in that direction like that, than there are in that direction, then you get that asymmetry, and the molecular collisions will start generating a torque. So it's a well-known effect. If you drop stones in water, they spin. There were these guys who did that as an experiment, Paddock and something, in the 1970s. They just got a big tank of water and kept dropping stones into it. And there's there's a shape factor that you apply to the torque. And it always comes out to about 10 to the minus 5. I don't know why. So when Luigi started studying, when he found the TAM collection, he did contact me to ask about cosmic spherules. And then he contacted me again to remind me to send him some stuff on cosmics. And then he contacted me again to remind me that I had forgotten to send him.
That's very nice.
And eventually I did send him my stuff. So, you know, that's why we write papers. People can learn from us by reading our papers. And you generally don't approach other scientists to find out about what they're doing unless you want to collaborate with them. I'm now becoming a bigger and bigger. The older I get, the more I want to collaborate because I'm lazy. No, because it's fun and it's more generous and it's egalitarian and I always think it was spreading the love. I love fieldwork and I quite like writing too. 100 years on cosmic dust. Oh. Well, who knows, really?
No, I know, nobody knows.
Well, I should think in the next few decades, we will get more and more space return samples. We will see more and more diversity within the asteroid belt. We may even receive cometary samples. And there will be attempts to collect interstellar dust again in space. We definitely sample return from Mars. But I think that will open up us collecting dust that's sleeting through our solar system, that we could study the rest of the galaxy. Because, of course, the big problem for us is we can't actually even get to the nearest star. That's out of our reach until some magical scientific discoveries made allowing us to do so. You know, you would have to have a lot of commitment to science to would be willing to get on a spaceship that you would not get off of, that your children would get off of. And then they'd probably want to be artists. You know. So I think the future of cosmic dust really is in studying the rest of our galaxy and really locking down what the diversity of materials is in our solar system. The way in which organic material was delivered to the Earth by micrometeorites has a direct influence on the origins of life. Because we still don't know much about that at all. We don't know about what the first living thing was, the first self-replicating organism, why it evolved why it appeared so quickly on the early Earth. We do know that the extraterrestrial flux was maybe 1 million times higher than it is now, with most of that being dust. There's one thing that you do need to have those primordial areas of surviving asteroids and comets in order to have a decent dust flux. But let's say you've got a planetary system where the giant planets have migrated too much and they've destroyed all the terrestrial planets and they've destroyed their asteroid belts and they've slung most of the comets out of that solar system, then even at an early stage you might not have much dust. So there are scenarios where you might not get that. The real test will be if we find life elsewhere in our solar system, because it means that the origins of life are spontaneous and probable given the right conditions. So, you know, I'm wishing for fish people on Europa or the oceans of Ganymede or something. Although when I was on the Infinite Monkey Cage with Brian Cox, he very much disagreed with me that there could be. He took me much too seriously. What do you mean that there's fish people swimming around? Oh, I don't think so. I really don't think so. Okay. It's a reducing ocean. And I talked to him afterwards, and he said, "Do you really think that there could be living things on Europa?" I said, "Yeah, Brian, why not?" And he said, "Because of this reducing ocean." I said, "The one paper has come out with a whole planet geochemical model, and you really think that's got a high degree of certainty? We don't know that ocean is that reducing. You know, it's one paper from a model that's got huge uncertainties. Yeah. So I wouldn't rule it out because of one paper." I do find that physicists, by the very nature of their training and their research, as opposed to geologists who can't do maths, have a much higher degree of confidence in modelling results. Yeah. And in particular, you know, I've had arguments with physicists, well, that can't be true because of my model. And I'm like, yeah, but what are the assumptions on your model? Because that's where the devil is. The maths can be perfect, the physics can be perfect, but if you've got the wrong assumptions from the beginning and the wrong boundary conditions, then the model can be entirely different. And how much phase space have you actually investigated with that model? Just a tiny little bit of it. And you've chosen where to run your model so you can get the result that you wanted. So I had a paper rejected from Nature Astronomy recently. It's a real shame. I was unlucky to have 4 reviewers, of which 3 were astrophysicists and 1 was a meteorites person. Okay. And the meteorites person really liked the paper, so this is brilliant, and I definitely published it. The 3 astrophysicists just tore it to pieces. Because I was talking about trying to place it in context of the early solar system. And they objected to it on the basis of, you know, this disagrees with my models of the early solar system. And the funny thing is all 3 of their models were different. I was like, you know, if you can't agree, don't object.
But you were also involved in the pioneering work of the fossil micrometeorite.
Yes, I started being interested in that during my postdoc, so that was 20 years ago. And I came across this paper, I think it was a guy called Much, I'm assuming they were male, in 1973. And they had recovered particles from salt that they said were micrometeorites. But scanning electron microscopes were in their infancy at the time. And you really couldn't tell. These could have been anything. You know, they didn't contain any nickel. But it was reading that paper, and I thought, oh, it probably could be. And I thought, well, maybe you can get it out of rocks. These were surface salts in the US. So, but at the time, I was studying the Antarctic micrometeorites, so I didn't have a lot of time to then start expanding it into something else. And I did a grant proposal on looking for micrometeorites in rocks that was turned down. And then a paper came out in Nature on finding micrometeorites in Paleoproterozoic sandstones in Finland. Well, this was the problem. So it turned out that paper was fake, that the scientist involved had salted the sample. He added micrometeorites from Greenland to the samples. So, but that just drove me on and made me think, well, maybe, okay, I know that this was faked, but I think you probably could, you know. And Susan Taylor did a paper, and she recovered micrometeorites from Jurassic hard grounds. This was really early. This was like 91. So that was even before me. I eventually put another grant in on it, and it was hilarious. I got turned down for it again. And this was for a fellowship. And I went into this, did the interview, and there was a panel of all the physicists who were asking me about my research proposal. And I was saying I was going to get deep sea sediments, and I was going to collect micrometeorites. One of these physicists said, so these deep sea sediments, are you going to use a submarine to collect them? And I said, no, we'll collect them on land. And they said, oh, surely that's not possible. How can there be deep sea sediments on land? And I was like, you do realize if you go to the top of Mount Everest, you'll find fossils of sea creatures. And she went, oh yes, of course. She said, plate tectonics. And I said, that's right. And I thought, I've not got this grant. I've not got. And as I walked out, with the interview finished, I'm walking out the door, and one of them went, oh, one last question. Which asteroids do these micrometeorites come from? And I looked over my shoulder and I just went, all of them, and walked out. And I just thought, there's no way I'm getting that. And I didn't. They turned me down for the grant. I put in for five grants on fossil micrometeorites now, and every single one of them has been turned down, saying this is impossible. And we've demonstrated it's possible. Well, you heard it from me. There was a PhD student at the Open University who did some, and they dissolved it of salt, and they found cosmic spherules. They were heavily altered, but they were quite nicely pseudomorphed by clay minerals. You could even make out the textures, but the mineralogy was completely changed. So I think Monica Grady wants to do that right now. I think Martin's involved with it, so I think they've gone off and done this. Unfortunately, so I was involved in that first study, and unfortunately the PhD student never published it. So it sounds like Monica's doing it again. But they're not good. It's not good places to get lovely micrometeorites. A lot of those highly saline lakes are filled with microbes that love to eat minerals. It's like the cryoconite, Michelle's cryoconite. You know, the bacteria there sit there and eat minerals. They eat all those S-type micrometeorites.
From his descriptions, I almost see it.
Yeah.
The woven carpets of...
It was horrible, absolutely horrible stuff.
Horrible stuff, exactly.
Slime.
But it seems like the chalk ones from here, and could be from Denmark as well, they are quite pristine.
Yes. Well, yes and no. So they look lovely, and one or two of them has metal, but they have chemically exchanged with the...
Yeah, I read the
manganese in many of them. In Denmark, we're starting to find aluminium-bearing magnesite, but with, you know, just fantastic textures that are pretty much got to be micrometeorites. It looks like it's still a very hostile environment. And whether that happens during diagenesis, early diagenesis, or... So yes, you can find them, but there is a limit to how you can interpret them, and most of the S-types go. You know, Martin found one in the chalk that was an absolute pristine barred olivine spherular. Looked like it came out of the Antarctic. And, you know, I did make sure that we questioned whether there was any possibility that this was an Antarctic micrometeorite that somehow made it into the sample, but there didn't really seem to be any chance of that. So, and all I could think was that it had become trapped in an early cement and it just got encased in calcite and so survived. But I've yet to find another one of those, despite looking for them. And if you talk to Martin did this study of Monte Corvi and dissolved and crushed up and dissolved 127 kilograms and found like 5 micrometeorites. We don't understand it. I don't understand it because those were in miles, and we took in Denmark the background. You take a kilogram, crunch up a kilogram, and you'll find up to 10. That's what we expect to find. Martin's just minimal. Don't know why.
No, but there are in the urban collecting business. There are some still the reason why we on one roof find 400, and the neighbor building 0, and they have been there for not exactly the neighbor, but let's say a couple of 100 meters away.
Weird, isn't it?
Where and I suspect it's the ground turbulence in the
winnowing.
Like between large buildings, there will be a lot of turbulence and change the trajectory of the particles before landing at the elephant's graveyard somewhere.
One of the things I thought was an amusing idea. You know that there are some water nymphs, these little creatures that build their shells out of mineral grains, and some of them have a preference for magnetite. So I wonder if they concentrate micrometeorites. So you can imagine these creatures wearing cosmic shells.
Any message for your fans?
Well, to my mother, I would say she is my only fan. So
no, you're wrong. Because now there are every month 10 new micrometeorite hunters.
Oh, really?
Successful ones. And they are getting so much better at photography and organizing tediously their collection, etc.
Well, we are
a lot. You have a lot of fans.
We are seeing more and more papers appear on micrometeorites collected on rooftops, on mountain tops. So one of those aluminium copper things was from the top of a mountain. This drain pipe in the Congo. Keep looking. We want to see some more really rare particles. Look for things that are definitely micrometeorites, but that have got odd things in them. In Ryugu, they reported finding fluid inclusions in sphalerite, and some of the fluid inclusions were CO2 dominated, and they used that. They suggested that meant the asteroid had CO2 ice within it, which is rubbish. Well, that's presuming that the only way you could get CO2-dominated fluids is by having CO2 ice. But I can buy a bottle of Coke and have CO2-rich fluids exsolve from them. So if you look at the paper, it was a paper by Ito on Ryugu. They have one statement saying, and we looked at these fluid inclusions and found they contained a CO2-dominated fluid. And I was like, where's your data? No data at all. It was published in Nature Astronomy, and it was just this one throwaway statement. And it really annoys me because people keep bringing it up when I talk about ice and asteroids. They're like, well, they've proven that there was CO2 ice in Ryugu. I'm like, no, they haven't. They've shown that they've mentioned that there are some fluid inclusions that contain CO2. They haven't even told us how much CO2. I've written 4 papers now on Ryugu, and these are the ones that keep being rejected from Nature Astronomy. So we found this is where we found that large chondrule in Ryugu, and that's where got rejected from geology. Oh yes, well that's what I've been rewriting this weekend. I rewrite it and then send it to another journal. Some require more rewriting than others. If you want to publish in high-profile journals, often, because the editing is so bad, it will get rejected for pretty much no reason, and then you try the next one, and then you rewrite it for the next one, and then the next one, and hopefully eventually it will be published, and if it doesn't, you just go, oh, darn it, I'll send it to MAPS. So eventually it gets published. They are the highly selective journals that rejects more papers than they publish. So Geochimica publishes most of the papers it receives eventually, but it does have a rigorous peer review process. Earth and Planetary Science Letters, that rejects maybe 50% of papers that it receives,
Okay.
but that's not considered high profile. So geology rejects 90% of the papers, and that's all that is. For years and years and years, I just published everything in meteoritics and planetary science. And it was only after a while that I thought, oh, I'll try and submit this to geology. And it went straight through. And I thought, so all of those papers I could have sent to a high-profile journal. And I never even thought of it. It doesn't really matter to me, but it's the, you know, if I ever want to get promoted, then one of the criteria I can use is, well, I've got all these high-profile papers. And it's a way of demonstrating quality. It's been a long time since I've gone to the library and actually read a hard copy version of a paper. It's all electronic these days, available on demand. Nature Communications is only online. Yeah, and of course, it's a license to print money, because we work for free, we review it for free, and then we pay for it to read it. Yeah. Or our universities do. One of the wonderful things about it is it can be one of the first in-depth contacts children have with science. Something that they can do on their own. You know, if they do become scientists, they won't be studying cosmic dust, but they might, you know, they might work out faster than light travel, you know, or something like that.
Catholic world.
Well, this is the big problem with the internet, isn't it? It's made everybody think they are an expert, because they've got no, because you need a lot of experience, and in order to be able to identify what's rubbish. And there's more rubbish out there than there ever has been before. I've always had to deal with conspiracy theorists all the way through my career, because, you know, from the moment I started studying meteorites and cosmic dust, it just attracts people who, conspiracy theorists. So, but at first it was very rare. It was only stuff like the NASA never landed on the moon conspiracy theory. Yeah. But I've noticed it's now getting extreme. Everything is a conspiracy theory.